Hello everyone, this is Yazan. In this presentation, I will talk briefly about the motion orchestration meant to be used in one-stage wafer scanners. I will start by briefly describing its dynamics and the concept of stationary center of gravity, followed by the needed requirements for suitable motion profiles that maintain stationary center of gravity along with some examples. After that, a proposed new conceptual design is introduced as well as its associated vital quantities. Then the simulation results will be discussed, followed by some concluding remarks. In general, dual-stage wafer scanners combine the precise utilization of motion and light to produce integrated circuits. Compared to other single-stage wafer scanners used in semiconductor manufacturing, the dual-stage wafer scanners have higher throughput and therefore studying their performance is more challenging. A dual-stage wafer scanner executes multiple tasks in parallel to increase the machine throughput. Namely, step-and measures, step-and scans, swap, load and load wafer substrates, and reticle patterns are the main tasks involved in such machines. Sharing the same time and physical space, chain interaction is inevitable during the aforementioned tasks. At all times, the optics chain must be held stationary. To that end, balanced masses are usually used with extreme caution about their needed physical workspaces. According to Newton-Euler equations of motion, the motion of a body can be characterized by the driven stage mass properties, applied forces, and moments. Besides inducing linear motion, when applied at a distance from the stage center of gravity, the forces create moment and stimulate angular motion that is responsible for the angular vibration and the desired motion coupling between the interconnected stages. The same can happen at the chain's level when they faithfully follow poorly designed reference trajectories. Usually, the reference trajectories can be designed using very simple shaping techniques. The whole system can be approximated as a system of particles with point masses, and therefore a Newton-Euler equation is applicable. The net force and moment about the machine center of gravity is given by the equation over here. In this study, we have the balanced masses actuated and accelerate in the opposite direction relative to their associated stages. Utilizing this and solving for the acceleration kinematical quantities yield the nonlinear differential equation shown here. Now it's desired to find acceleration profiles that maintain stationary center of gravity. Two examples of continuous time piecewise trajectories are depicted in the figure shown here, namely the sine-sine and sine-cosine. The stepping motion of the step and scan and the step and measure tasks using the symmetric sine-sine trajectory is given during the non-zero acceleration periods for other than the first die as shown over here. Also, the vital quantities of the two tasks are provided. To stretch the benefits of the proposed approach towards the machine design process, let's consider the case where additional masses are to be totally avoided. The main idea behind the proposed conceptual design depicted in this figure is to utilize the involved stages as balanced masses to each other under suitably designed machine or motion orchestration that maintains the stationary center of gravity of the whole machine. It's clear that the two tasks share the same step size, while the measure task can cover more dies compared to the scan task proportional to the value of C, which is assumed to be greater than 1. Interestingly, with large C values, the measure task can be finished before the scan task actually concludes, having M1 perceivably idle while the measurements are being processed, switching to another orchestra involving only M4 and M7 designed as outlined previously might be needed. The full balanced mass case was simulated using the following parameters, along with the motion orchestra shown at the middle under the sine-sine trajectory. The resulting acceleration profiles of wafer 1 stage, for example, are shown here to the right, where an operation time of approximately 0.3 seconds per die was needed. The overall machine throughput according to the shown orchestra was about 17.85 seconds per wafer. The no balanced mass case was simulated using the same parameters under the sine-cosine trajectory with the additional parameters shown over here. The resulting motion profile of wafer 2 stage during the scanning phase of one die is shown in this figure. In conclusion, we approached the reference motion design problem for dual stage wafer scans from a geometrical perspective, where the motion stages are treated ideally as a system of moving point masses. Mainly two tasks were of interest, step and scan and step and measure, where a well-designed reference trajectory is capable of steering the motion of the machine while minimizing or completely eliminating any residual vibration, while respecting the machine geometrical, structural, kinetical nature, and dynamical features, and meeting the other imposed operational constraints. Failing to meet the criteria presented here, the machine dynamics will misbehave whenever it follows the design trajectories faithfully, which leads to performance degradation. Thank you.